Thank you all for joining us today for this week's virtual panel, Understanding the World of Simulation. After the panel ends, you'll be able to find the full recording and all our previous virtual panels on our website at www.pavecampaign.org, or follow us on social media at PAVE Campaign to keep up with all of our work in the AV space. My name is Tabitha Colter, and I'm PAVE's Director of Operations and your moderator for today's panel. Today is our third panel in March, where we're focused on looking at the technology that powers automated vehicles, how they perceive, understand, and navigate the world. Today, we'll be looking at simulation testing, the various forms it takes, roles it plays, and techniques it enables. With me today are three incredible panelists from PAVE members Kodiak, Applied Intuition, and NVIDIA. First up, we have Matt Cragun, Senior Product Manager at NVIDIA. Matt, welcome. And our second panelist is Andy Wendel, VP of Engineering at Kodiak Robotics. Andy, great to have you here with us.
Thanks for having me, Tabitha.
And our third panelist is Varun Mittal, Head of Customers and Application Engineering at Applied Intuition. Varun, thanks for joining us today.
Thanks for having me.
Absolutely. So thank you again, gentlemen, for joining us today for this important deep dive into simulation technology. This technology is often a crucial part of developing and testing AVs, and we're excited to provide a look at how it works to our audience today. So to help provide that look at this technology, I'd actually like to introduce a special fourth panelist. In the fourth panelist box you see on your screen now, we're actually going to show a few short video clips and have our panelists talk about what you're seeing as a way to give a visual introduction to this technology. Andy with Kodiak and Varun with Applied work together to use simulation to test Kodiak's applied trucking. So they'll be walking you through a quick intro on how that works before we return to our usual panel format. So to start us off, Andy, could you explain how, as an AV developer, Kodiak uses simulation and how it interacts with real-world testing?
Absolutely, yeah. We use simulation actually throughout our entire development. So at Kodiak, we develop AV tracking for medium to long haul deliveries. And what you see here on our fourth panelist is actually a video from our truck. The green band that you see is the trajectory that the truck takes. You also see all the other vehicles around us. And what happens in this particular scene, and you see the video looping, is that a vehicle that was driving in front of us actually just suddenly pulled over. It probably had some problem and it pulled over to the side of the road. And while the reaction that our truck had here was good, we felt like, oh, we can actually go and improve this a little. We can probably react sooner and lane change over just a bit sooner. So we wanted to take this case into simulation and see how we can improve it further.
That sounds really interesting. Varun, could you explain a little bit how that works?
Yeah, absolutely. So what you're seeing in the video now that will come up is that same scenario which Andy just showed, that's actually been brought into simulation. This is log-based simulation or resimulation in this case. Everything is being replayed back exactly as it was seen in the real world. So even though this looks like a simple animation here, the truck actually thinks it's in the real world, so very much like Matrix, and it's making the same decisions as it would in the real world. So this is a pretty effective way to test software and actually make changes to it over time.
And Andy, what does that help enable?
Yeah, once we have recreated this scenario in simulation, we can really go and start experimenting with changes to our implementation here. So really the development work starts now. And we go and in this case, work on our perception algorithms and look at how we can improve them, how we can maybe detect the deceleration of that vehicle and pulling over into the shoulder just a bit earlier and therefore initiate our lane change earlier. And so what you see here is actually two different trucks. On the bottom, on the bottom, you see this yellow ghost truck. You'll see it in a second again. The yellow ghost truck is really what happened in the log, and the red and white truck is what is happening in the simulation after we made our changes. So we have the possibility to really compare the two behaviors, what happened in the log at the actual time when the vehicle was out on the road, and what happens now with the improvements to the code that we did. And that is very powerful, right? It lets us actually test different ways of improving our system. It lets us see what the behavior would be after that fix.
And as we're thinking about those different scenarios that you can map, it makes me wonder, how flexible is the system? Are you tied to those underlying perception logs, like the yellow ghost truck you were talking about?
No, we're not. So there's a bunch of different ways of actually creating simulations. But for this one specifically, like Varun said, it is a log-based one. And the log-based ones we can also augment. So here you see a simulation where we added a vehicle that was not actually on the road at the time when the log was collected. And we've put it to our left side in the lane where we were actually lane changing into. And now that really prevents a lane change. And we wanted to see what would the vehicle do in this case. Of course, we programmed it to do the right thing. And so we know what it's supposed to do, but we wanted to know, does it do the right thing always? And in this case, it actually now slows down and nudges over just a little, but it does not actually lane change anymore. And so augmentations like this are really powerful for us to test various different scenarios, to go and take one case that we have discovered on the road in the real world and create a lot of different cases around it. You could imagine lots of different variations here, us just being closer to the vehicle when that vehicle pulls over to the shoulder, the vehicle next to us maybe cutting us off. You could do all of these simulations. And that is only possible really in simulation.
That's fascinating. And Varun, these simulations are really interesting to watch, but they do look pretty rudimentary in terms of what they're portraying. And I know that there are other simulation videos that look more like video games. What's the difference between those two types of simulations?
Yeah, I mean, each different type of simulation is important depending on which part of the autonomy stack is being tested. So if you're testing the decision making or the controls of the truck, that's where you need the object level simulation, which we showed earlier. But if you are testing a perception system, then you do need to render the surrounding cameras, the LiDAR, the radar that are in the scene. And what you're seeing in the video currently is an example of camera simulation here. The same log that Andy showed earlier in the real world, that's been actually recreated now in simulation to recreate the locations of objects, the location of the vehicle on the side. What's great about this is you can actually now change everything. You can change, time of day, you can change anything you'd want to actually test the system.
That's fascinating. And Andy, can you give an example of how you'd use that more video game style in development?
Yeah, like Varun just said, for instance, we could change the scene to be a night scene, as you can see it in the video here. We could also look at different weather conditions. We can simulate rain, we can simulate fog, and these conditions just change quite a bit how you would perceive the vehicle, how also a human driver, of course, in foggy conditions would perceive that same scene. And we can go and look at how our driver would react to that. And so this is particularly useful for machine learning models. It is what is called kind of a closed loop simulation. Since you know all of the different parts of this simulation, you can automatically create, for instance, a ground truth. You know where the objects are placed and when you should react. So that's very useful. Overall, this is still, though, a smaller part of the simulation efforts that we do. We use mostly these log-based simulations and sometimes even just some fuzzing or variation around those, where we go and import things that we have seen on the road. We bring them into simulation. We use that to really check some of the edge cases. And very importantly, we use that to prevent regressions. So once we have actually done the code change and we figured out the behavior that we're happy with, we now can put observers on these and can say, let's make sure this same behavior always keeps happening and that we're not regressing from that. And that really increases the development speed. And in our case for Kodiak, we've recently been able to do completely disengage-free deliveries on our Dallas to Houston stretch in Texas for customers. And that was enabled really by doing simulations like this and being very diligent about not having any regressions in the development.
That's great. And thank you both. And thank you to our guest, fourth panel video, for helping to give us that demonstration. Now, Matt, as we move back to a more discussion style, I wanted to bring you in to help talk about the bigger picture of simulation through your experience at NVIDIA. What are some of the biggest benefits of using simulation to develop automated driving systems?
That's a great question. So there are a couple of things. I think the first that Andreas and Varun did a really great job at illustrating is that the speed at which you can iterate is really fast. And so there are two really, with developing an autonomous vehicle, there are two really big costs. One of the costs is just dollars. How many dollars does it take you to develop a product? And we know that it's really large. And then the other one is how long does it take? And I think that that's the other challenge is everybody's hoping to get things hopefully on the road in a safe way as soon as possible. And the nice thing about simulation is it lets us move really quickly. So it lets us, like they mentioned, test a lot of different use cases, add a lot of variation, while at the same time making sure we don't have regressions. But at the same time, it lets us test things that we wouldn't normally be able to test, either because they're too expensive or because they're too dangerous. One of the challenges that you have if you have a safety driver is that when there's a situation that occurs that may be too dangerous to test, that situation may be really interesting. Your engineers may really want to know how does our system interact with a pedestrian. But if you don't have confidence in the system, you can't let that play out on the road. It's not a safe way to do that. But in the world of simulation, we have a lot of flexibility to test our decision making, to test our perception, and to do so and without a lot of the consequences that exist in the real world. And so the nice thing is that we're able to really cut down the cost because just the dollars. We can do so much more testing at a large scale. We can iterate much more quickly than we could if we had to go back to the vehicle every single time. And then we can test a lot of things that we couldn't, that we're just not able to test on the roadway.
Absolutely. And Varun, off of Matt's point there, how does simulation help ensure that you see the most important real world scenarios?
Yeah, absolutely. I mean, there are two major ways to use simulation with these real world logs. One is what we showed earlier. You find out that there is an issue, right? The developers look at an issue. There might be a triage team that finds an issue. Simulation can help you to recreate that scene very quickly and then do all the fuzzing and variations around it, as Andy was mentioning, to make sure that your system is going to robustly solve that issue. What you don't want is you have one issue, you make a software change where you think you've solved it, and then you see a small variation on that issue again tomorrow in the real world. So I think that's really important in terms of using simulation to debug and confirm that real world issues are solved. The other way where simulation is very powerful is if you have simple driving, quote unquote, places where the software work well, you also want to use simulation to test that newer versions of your software will really work well against those as well. So what that means is, let's say you have 5 hours of drive data where there wasn't a disengagement, you still want to use simulation against hours of that drive data to confirm that newer software versions will also continue to perform in that manner. And I think that's where, going back to a point Andy made, a lot of simulations do use the real world logs, and they use that both for solving issues, but also confirming that the software is going to have good performance.
That's right, yeah. And maybe to add to that, this is something where we often get the question, how many scenarios do you have? How many simulations are running? And actually, I think that the right question would be, how many useful ones do you have? Because you could go and actually create a lot of simulations and scenarios just by taking one of our logs and just creating for every 10 seconds snippets, create a scenario. But those probably wouldn't be very useful. So you really want to sample what you get from on-road discovery, to sample that and actually look at the interesting things there. Create simulations there. Simulations are not very cheap, as we heard. It's cheaper than on-road testing, but still it actually costs a lot if you run a lot of simulations. And so really focusing on the ones that actually provide a lot of value is a very good strategy there.
Yeah, and we received a number of audience questions asking about the mechanics of simulation, one of which I'd want to direct to you, Matt. One attendee asked, how do you integrate the physics of vehicle performance into simulation, such as tires on a wet road?
Yeah, that's a really good question. Obviously, simulation, Varun pointed out at the beginning that simulation is a model, right? And one of the tools that we want to make sure is that our model, or as a tool, that it reflects the real world, but we have different levels of fidelity as well. So if you look at vehicle dynamics models, they started everything from what's considered a simple bicycle model, all the way up to you can get into the vehicle dynamics world of F1 and racing, and they have really, really high performance vehicle dynamics models. The goal of the simulator is to be, in our opinion, is to be unopinionated about what you use. And so we have some simulations that we run where the vehicle dynamics are modeled simply, and some where we have very detailed models that we correlate against real world testing and on-road or on-track testing. And we plug those data in. As well, we also have times when we actually plug into third-party tools. So we have the ability to, for instance, run with third-party software such as DSpace ASM or IPG CarMaker, or some of the other tools that are on the market. And that's really helpful because if you go and talk to a lot of the teams, especially at larger OEMs or companies, they already have a lot of experience with their vehicle dynamics that they've gained over years. And so they understand really well how their vehicle performs on a wet piece of pavement. And so being able to take a model that they've already built and plug that into your simulation is really, really helpful. So we try to be able to leverage a wide variety of models, but also to make sure that we build on the experience that especially our automotive partners already have.
That's fantastic. And Varun, we got another similar audience question actually that asked, how do you model human-like pedestrian behavior in simulation? So, slightly different angle.
Yeah, no, absolutely. That's I think the approach for simulation and modeling for the pedestrian behavior is in some ways similar to the approach on vehicle dynamics that Matt just referred to. It is about having a tunable version of the model, right? So depending on your use case, if you're a developer trying to develop a software that will detect a pedestrian crossing a road, you want a simple model which will make that pedestrian go across the road at all times without worrying about, how would a real pedestrian behave right away, right? So we definitely provide models which are simple that a developer can put in and just have repeatable behavior. You do need the advanced behaviors though, eventually, so you can actually see, would your stack react correctly to all of the variations in the real world? So in terms of modeling those type of human interactions and human behaviors, there's several approaches that we use. There's everything looking at real world data and being able to replicate that data. There are also variations in terms of or approaches in terms of literature right now. There's a lot of work around capturing human behaviors, being able to model that. So it's a hard problem. We have several people in our team who work exclusively on that. But I wanted to highlight that this fidelity and this ability to tune the model is really, really important for each use case.
Yeah. And Andy, turning back to you now as an AV developer, how accurate and detailed do simulations need to be in order to be useful to automated driving developers?
Yeah, it's quite interesting that there's different levels of this. So you could think of also the questions you asked just before. There's maybe the OEM who wants to see what is my vehicle stability, right? And you want to model it really down to the nuts and bolts. And then it goes further up the stack to at some point really high level behaviors. And at that point, while your actual model, let's say a pedestrian model or another vehicle model around you, while that needs to be contained in that space, you actually want to capture the variance as well. So you would have a vehicle, usually vehicles are braking at a certain deceleration in front of you. That's great if you find the perfect one and you want that to be contained. But you want to vary that because our truck in this case should be safe to people braking harder and people braking not as hard. So you really want that variance in your simulations. And that's why it's not that important that all the other actors are exactly modeled, but that our technology is able to deal with that. On the other hand, though, for our technology ourselves, we of course want the simulations to be very deterministic. So if our vehicle does something on the road, then in simulation, it should do the exact same thing. And a lot of testing goes into this. We can, on nominal cases, we can do what we just showed before. We can take actually a log and run it in simulation and see that the exact same thing happens. But then there's some more scenarios, like for instance, if you had a collision avoidance scenario that you would not want to let play out in the real road, that's where you go to track testing. You actually go and try to stage a very similar situation, and you make sure that your one simulation is very similar, and then you go and scale from that, right? Then you can go and add variations in your simulation, but you need to make sure that it's actually the behavior of your own software in simulation and on the road is deterministic.
And just adding a little bit onto a previous question on sensor simulation, right? It's the same approach there. How do you know a sensor simulation is good enough or not, right? For all of us as humans, right, we look at the video and we try to think of, does it look realistic or not, right? That ends up being our metric, but in the end, especially for autonomy developers, the real metric is it predicting the right performance of my algorithms similar to the real world? And the way we prove that out with our customers, there isn't one simple answer there. There is lab level tests confirming that the sensors are modeled correctly. There are algorithm level tests confirming that the algorithm performance across different weather conditions is the same in real versus kind of simulated world. So there's many, many levels to that simulation and validation. But I think that's where the use cases and how the tools are used become really important, rather than kind of the tool visual quality by itself, right? I think that's where the industry has been for some time, where people were just putting out videos of like, hey, this looks better than this other video. But the neural nets don't just look at the video quality, right? It is really about the details.
Yeah, and we had a panel earlier in the year where we discussed safety cases and how the structured argument supported by evidence can help justify the safety of a system for application in an operating environment. Safety cases can have many different elements of evidence to help demonstrate safety of a system, one of which can be simulation. Matt, I was wondering if you could talk about how simulation helps with an overall safety case in AV development.
Yeah, I think that's a great question. I think both Andy and Varun mentioned, some of the testing that needs to happen on the backside. The first step is really to build confidence in a tool. And as was mentioned earlier, simulation is a tool, and like any tool, it needs to be calibrated and it needs to be correlated. And you need to make sure that that when you go ahead and you do a real world test compared to your simulation, that you get answers that are the same, right? And that you feel good about. Because what happens, the real value of simulation is the ability to test things, especially in a safety context, that we can't test for various reasons. Oftentimes it's because it's too dangerous in the real world to do so, but to test some of those things in simulation that you can't test in the real world. And so to be able to gain the confidence that your simulation is good, you have to somehow ground it in reality. And so a lot of this work that Andy and Varun mentioned is really the fundamental work that needs to take place. And it's really more than just, it's really about how the tool gets used, and as much as it is about the tool that it itself. And so this is, as we work internally with customers on using simulation, there's a lot of effort that goes into how do you assess the performance of the tool and make sure that you have things modeled appropriately, and where there are gaps, because no model is perfect, that you understand what those gaps are and where the trade-offs are that you're making in terms of fidelity and other things. So a lot of it really just goes into doing your homework. And then on top of it, we're actually at NVIDIA, we're working very closely with some of the regulatory bodies at the UNECE and US Department of Transportation as they start to consider thinking about new ways to approve autonomous vehicles and how to regulate this functionality. That simulation is, we hope and we believe, needs to be one of the factors considered as those regulations get drafted. And so we're trying to understand what the needs are and trying to make sure that we can provide tools and best practices that will be useful.
That's great. Varun, anything else to add there about what Matt just said about safety cases and simulation?
I mean, all of the things that Matt mentioned make sense. I mean, this is our approach as well, including working with regulators, working with certification agencies to make sure we're using the best practices. And and even educating some of those agencies on that. The only other thing I would add is when you think about autonomy, there are definitely hazardous situations which haven't been accounted for. So there are known hazardous situations and unknown ones, right? The goal with simulation in terms of building the safety cases to reduce the unknown hazardous situations by taking maybe a incident that was seen, for example, the video we showed earlier, and then making many variations around it, so the unknowns are reduced. Or it might be if a developer thinks about a corner case, they can test many variations around that. So I think simulation really helps in reducing those kind of unknown hazards. And I think that's where really advanced programs are using simulation for safety.
Yeah, and I couldn't agree more with that, just from an application perspective, right? My background is that I was at Waymo for 5 years, working with a then very small team on actually getting the first vehicles out on the road, the first driverless vehicles. And in that experience, and the same at Kodiak, like simulation has just been critical to actually make that safety case. And really how we used the tool is very important.
Actually, off of kind of a point that Varun just made, Andy, one criticism that we hear of simulation and AV development is that it can't generate those bizarre edge cases that are sometimes believed to be one of the main challenges for AV systems. How would you respond to that?
Yeah, I haven't really heard that one. I think my experience is the contrary of that. So we can actually create a lot of edge cases there. And maybe the point that some people make is that simulation alone is not enough. And I would agree with that. There's different pillars, right, to actually build your safety case. So we do real world testing. We drive our trucks to actually get that discovery. Our safety drivers are encouraged to always take over. So even though we did some disengage free runs, it's not because we tell our safety drivers not to take over. Of course not. Safety is really the most important thing in this industry for everyone. And it is one of the pillars of Kodiak's philosophy. And so the disengages that occur, they're often for comfort, or they sometimes they are actually for something that we need to fix really on our system. And so we take those as discovery. And then in simulation, we can actually go and fuss this some more, create variations around it. And then there's all the track testing. And all of these together, they create different edge cases, right? Like you see different things. For instance, in Texas, we see sometimes windmill blades passing us. And there are these really long vehicles that just don't look like a vehicle at all. And these are great edge cases that I would not have thought of if I had just created a simulation.
Yeah. Well, we're unfortunately running close to time. So Matt, I want to end on one final question for you, sort of looking ahead into the future. How do you see the future of simulation as a tool for automated driving system development? You know, are there boundaries to be broken and new frontiers to explore, or is it a fairly mature technology at this point?
Well, I hope it's not too mature, because otherwise I have to look for another job. But realistically, I think that there's a lot of opportunities in simulation. I think that the technologies that exist around our models, the way that we model sensors, the way that we model behaviors of people and pedestrians and traffic, there's just so much room for growth there. Other places are things like, how do you generate new scenes and new worlds to drive in really quickly? There's a lot of opportunity there. And then there is a lot of opportunity just around sensors. How do you get your visual fidelity, and how do you get the fidelity of your synthetic sensor data to be on par with real world, and make it look and perceived by the perception systems as if it was driving in the real world? And we get better and better, but there's so much more room. We're really excited at GTC that we have coming up to really make some share with the world some new announcements that we have, and some new technology that we have to hopefully push it even further. And that's what really makes me excited every day, is to come to work and figure out what are the next things that we can do to take the technology one or two steps further.
That's great. And that's sadly the end of our time together. But Varun, Matt, Andy, thank you all again for taking the time to join us this afternoon.
Thanks a lot.
Thanks so much.
Thank you.
Yeah. And thank you to our live audience for joining us again this week, and especially everybody who submitted questions in advance. If you'd like to follow up with us at PAVE or one of the panelists on this topic, please reach out to us via our website contact form at pavecampaign.com/contact or reply to your registration email. As a reminder, we will be posting the full video recording of this panel on our YouTube channel and website later this afternoon. Follow us on any social media at PAVE Campaign to see that as soon as it's released. And don't forget to join us next week for our next March panel looking at AV technology, a look at AV perception. Registration is now available on our website. Thank you all.